Yes, so we are going to talk about queues. Queue is again a very practical data structure. You see it, right? That let's say there is a queue of people to, let's say, get into a room, to get inside a, let's say, hotel. Okay, then if a new guy comes and if he tries to get in between here or here, then these guys will kick that guy out, right? Because they won't allow him to do that. So if you come last, you stand at last and you get in last. If you come first, you get in first. Okay, so it is like whoever comes in first goes in also. Let's call this out instead of calling this in. Whoever comes in first, that goes out first, and whoever comes in last, that goes out last. Okay, so if a new guy comes, he comes over here. So there are two ends of a queue. So there is one end from where things are removed, and there is one end at which things are added. So it is a dynamic data structure whose both the ends are flexible, both the ends can move, right? So that is a huge difference between stack and queues. So in stack, one end was fixed and both push and pop were supposed to happen at the same end. But in queue, that's not the case. If push happens at, let's say, this end, then pop should happen from this end. Similarly, if push happens at this end, then pop should happen from the other end. That is the most important distinction between stack and queues. I think a very simple example could be, let's say there is a server, okay, and let's say this is a Google server, and then there are many people who are sending requests to it, right? So although there are many policies, there are many different ways of handling requests, but one way is first in, first out. So whichever request comes first, that will be catered first, and whichever came last, that should be catered in the end, right? So it maintains a queue of requests, and now every request is an object. It could be an HTTP request. Okay, so every request is an HTTP object, and they are waiting in a line to be processed one after the other. So it is an extremely practical data structure, just like stacks. Okay, so how does it look like? So let's say there is an array, and in that array, let's say initially it was empty and you pushed 1, 2, 3, 4, 9. So clearly what is happening is that whenever I push something, that is getting pushed at this end. So let's say now if I push 15, this 15 should get pushed at this end. Okay, and now let's say if at this point of time I am calling pop, can you tell me which element should be kicked out? So the element to be kicked out should be this element. Okay, now let's say again you call push of 5, so I should have a 5 appearing over here. And then again, let's say if you call pop, then this thing should get out. So how many ends are there? This is a double-ended data structure. So some people call this end as front, and we will also be calling this end as front, and they call this end as rear. So this is your front and this is your rear. And what basically happens is whenever you call push of something, let's say you call push of 7, guys, those of you who have never implemented queues, it's my sincere request, please implement it at least once today itself. Okay, I understand it looks trivial, but there are certain edge cases to it. Okay, and we'll come over to those. So I want you to implement it before you start using your own version of, before you start using STL's version of queue. So whenever push of something happens, then the first thing that happens under the hood is, or which you are supposed to do if you are using an array to implement it, you will do rear plus plus. So by that, rear will start pointing over here, and then at this slot in the array you will insert this element. Okay, and whenever pop happens, then what should be done? Can you tell me what should be done? So simply I should move my front, simply I should do my front plus plus. So one thing is clear to understand, whether I am pushing element or popping element, these both pointers, which are my front and rear, are always moving in one direction only. I mean, it is never ever happening that front went ahead and then again came back. It is never like that. So both my data structure, both my pointers are moving in just one direction, and this will bring about one very important observation about queues. Okay, so but before that, tell me, if I need to declare a struct corresponding to queue, can somebody tell me what all it should contain apart from the array? Let's say I'm implementing queue using an array, and somebody assures me that, hey, this much size will be enough. Let's say somebody tells me that. Yeah, I need 2 pointers over here. I need a front and I need a rear. Very good. So I need a front and I need a rear. And let's say then I performed a declaration, then 1000 memory for integers and 2 memory for f and r will be allocated. So initially my queue is empty. So when my stack was empty, I used to initialize my top as -1, correct? Can you tell me how should I initialize my front and rear in this case? You have just declared your queue. How do you initialize your front and rear? Yes, very good. So both of them can be thought of as -1. There are other ways also to do that. There are different ways, but you can do something like this also. Q dot front equals to -1 and Q dot rear equals to -1. But now you have to be careful about one thing, because in general, you either increment your front or you increment your rear. In generic cases, does it ever happen that you increment both front and rear? It never happens like that, right? But whenever you are inserting an element for the first time, it's just for the first time. Whenever you are inserting an element for the first time, and you can check that, if q dot front and q dot r both are equal to -1, in that case, you should do q dot front plus plus as well as q dot rear plus plus. And then because your insertion happens at rear end, so you can do array of basically q dot array of q dot rear equals to whatever you want to insert, right? So what will happen as a result of that? Your both front and rear are pointing to index 0, and you just inserted an element, let's say 5 over here. Okay. Now let's say again you inserted 7, so 7 came over here, and your rear pointer will change. It will come here. Then let's say you inserted 11, you inserted 25, so this rear pointer basically will come over here. So your front is 0 and your rear over here is 3. Okay, this is how it looks like. Now let's just take a case. Let's just take a case. So let's say somebody inserted 35, and now this little thing came over here, and this is 4. Now let's say somebody called a pop. So this thing comes here, then again pop, so it comes over here. So you know, the interesting area for me, for in which my essential elements are lying, that is only from F to R. So nothing behind F or nothing in front of R is something which is of my use. Okay, cool. At this point of time, if somebody calls, let's say pop, then again this should start pointing over here. Can you tell me what will happen if somebody calls a pop over here? If he calls a pop over here, now this thing will become 5, and this will start pointing to this. So this is a scenario where your front has become greater than rear. Can you tell me what does it even mean? When your front has become greater than rear, what does it mean? It means that the queue is empty, yes or no? Yes, very good. It means that the queue is empty. I might have space left over. So let's say this array is long, I might have space left over, but my queue is empty. So if at this point of time somebody calls a pop, I should send him which kind of message? I should send him underflow message that, hey, you cannot pop anything because the queue does not contain anything. So let's say somebody instead calls a push of 1 now. So what will happen now, because push has been called, so rear pointer will be incremented, and now this also becomes 5, and both of them are pointing to this slot, and I have a 1 over here. So this is how things happen. So F greater than R, and basically F will be equal to R plus 1. Whenever it happens, your F will be equals to R plus 1. So whenever this kind of scenario happens, it basically means that it is your underflow scenario and your queue is empty. Okay. Can somebody tell me overflow scenario? Let us assume the size of array is n. So in such circumstances, what will be my overflow scenario? So just think of it in this way. If let's say the array was just of this much of size, and now let's say you called a push of 11. So what would happen? 11 would come here, and now your rear pointer would come at this, which is n minus 1. So whenever you see that your rear is equal to n minus 1, can I say that I cannot accommodate any other element? Because to accommodate any other element, I'll have to put it at rear plus 1, which is n, and index n does not exist. So can I simply say that the moment r is equal to n minus 1, whenever I detect r is equal to n minus 1, I will say that, hey, this is an overflow scenario. Yes or no? Right? Okay. Is something which is bad about this? Can you see something bad? Would you want to comment something about space efficiency? We had talked about this thing. Yes, space efficiency is very low over here. Yes or no? Because now you are saying that, hey, you have an overflow situation, but in reality, you are just using 2 slots in the array and the other slots are empty. So you're not reusing them. You're not recycling and reusing your space, which you should ideally be doing. Okay, so this is something which is bad about the array implementation of Q. So I'll be more specific. Linear array, in which you envision an array as a single line and then implement your Q using a linear array. This space efficiency is bad in that. Was this happening with stack? While I was trying to implement a simple stack, was something like this happening? It wasn't happening, right? Yes or no? It wasn't. Why? Because in that, one end was strictly fixed. Okay, what is the way to make this better? This is a very simple way, and I think you would have studied also. So what is the way to cure this space efficiency thing? Circular queue. Yeah, very, very important data structure, and that is how many implementations of queue are done. I mean, not all, but some implementations, because there is scope for better implementation also. That's why I'm saying that. Let us understand how would that be getting done. So what that does is, that says that, hey, if you have an array of, let's say, size, how much? Let's say size 5, and indices are from 0 to 4. So just fold it like this. So convert it into a circle. So if you do like that, you just have connected this end to this end by folding it like that. So now it is going to look, I think, something like this. 1, 2, 3. I think I need one more. Yeah, it is going to look something like this. So this is your index 0, this is your index 1, this is 2, this is 3, this is 4. So in that, what is going to happen? Let's say you push first element, so it comes over here. See, it's just that the way to look at the things have got changed, but in reality it is a linear array only. I'm just envisioning it as something like this. So let's say you push 5, then you push 7, then you push 15, then you push 11, then you push 1. Okay, and at this point of time, if let's say you call pop, then this thing is going to get out, right? Had it been a linear array, had it been your previous implementation, and then at this point of time, if I would have called, let's say, push of 111, what would have happened? Would I have been allowed to push this 111? I would not, right? Why not? Because my rear end is at n minus 1. But in this case you can. How you can? Because if you have indices from 0 to I minus 1, then it basically means that if you do I minus 1 plus 1 mod I, then all that you are going to get is 0. That is the thing over here. So basically, see, your next index would have been 5. Okay, but this 0 is nothing but 5 mod 5. Similarly, if you are moving from here like this, your next index here would have been 6, and this 1 is 6 mod 5. This 2 is 7 mod 5. So this is the point over here. So what you can do is, you can simply do, instead of doing rear equals to rear plus 1, you can do rear equals to rear plus 1 modulus n. Okay, so that way when you do it at this rear equals to 4, your new rear will become equal to 0, and now you can push this 111 over here. So now at this point of time, what happens, that your front is lying over here and your rear is lying actually over here. So this is the case over here, and the same thing. So if you are changing your f, you are doing this, And if you're changing your R, you are doing this. So you're not just incrementing it, you're also taking modulus n, because if you do modulus n, then you can recycle the space that you had left behind, and that also in the proper sequential order. Okay, now this is very interesting. At this point of time, let's say some guy says, hey, push 100. What should I do? Can I push 100 over here? I cannot push, right? Because if you take a look, my entire circular queue is full from this front, which is at index 1 till here. It is full. I do not have a single slot which is empty. So how do I detect overflow? So instead of having R and F over here, I could have had R over here and F over here also. So if you see that your F mod n is equals to R plus 1 mod n, then you can simply say that, hey, the overflow has happened, but can you tell me what will be the condition for underflow? Let's make underflow happen, okay? Let us all make underflow happen. So let us do some pops, okay? Let's say you call a pop, this thing is gone, front comes here, again call a pop, this thing is gone, again call a pop, this thing is gone, again, yeah, so now your front would basically be here. Can you tell me how many elements are there in your queue right now? At this point of time, how many elements are actually there in your queue? 2 elements, right? Which is this 1 and 111. Let's say you call pop again, so this again goes, and now your front comes here. Let's say you call pop again. When you call pop again, this front will come over here, yes or no? How many elements do you have in your queue right now? 0. And is the condition same? Is the condition same that front is lying in clockwise just to the right of this R, yes or no? So don't you think it is hard to distinguish overflow from underflow in circular queue? Will you be able to make sure that which one is overflow and which one is underflow based on this expression? I can't do it, right? Okay, there is a very simple solution to this, a very simple and very elegant solution to this. How many elements will be there when the overflow situation is actually happening? And how many elements will be there when underflow situation is actually happening? Can I say 0? Yes. So why not keep a track of number of elements in the queue? I can do that, right? So you can have one more variable at your structure called as size. And whenever you push something, you do size plus plus. And whenever you pop something, you do size minus minus. So instead of relying on the relationship between F and R, you can simply check the value of size. If size is equal to 0, that is your underflow situation. And if it is n, then it is your overflow situation, right? So there are many ways to do this, but this is a very simple and easy way to just track it. The good thing about circular queue is that it recycles the space, okay?